want to welcome you to another exciting statistical topic. Of course, statistics is like a story that goes on and on and on. And you know what? It's more or less like a movie, very interesting movie, where scenes are kind of connected. You may need to be able to understand what you've done before for you to be able to follow through. And that is the reason why I'm actually going to say, in case you need clarification, I will advise that you reach out. I'm approachable and flexible. And at times if I record, like I'm recording this now, if you just go to YouTube and put my name, of course, you're going to have access to some of my recordings. Okay, so I want to welcome you to this topic. Today we are studying what I call sampling distribution related to norma. So this material is already uploaded. I uploaded this material yesterday. You can check. I put some updates. Okay, so in the headline, I'm going to I'm going to have a kind of recap on law of large number. Of course, you know the other time I walk you through law of like numbers. I'm going to have a recap on that so that you'll be able to see how the law of large number is also related to the use of empirical rule and Chebyshev rule. Okay, then I'm going to walk you through the Chebyshev rule and empirical rule, and lastly, application. Of course, we're always going to have application. What is the essence of what we're learning without, if there is no way we can apply that, of course, we're just learning for fun, so we're not going to learn for fun. There's always going to be application. Okay, I just need you to sit back, be focused, and if there's any area that you need clarification on, please do not hesitate to ask question. Okay, so I want to first, let me revisit law of large number. Of course, we did that in the last class, and I remember I demonstrated this theoretically, and even I cited the application of this in businesses and industries, and the reason why in research we need to encourage researchers to take a sufficiently large sample. Okay, so the idea is just that, okay, the whole thing started by trying to estimate, trying to figure out unknown parameter. The parameter could be average, parameter could be proportion, parameter could be variance, standard deviation. Of course, anything that has any population characteristics that we seek to determine, we don't know them right now. Okay, it could be average, annual average income in a particular country. It could be what is the numbers of Americans that approve the job the president is doing. That is parameter. And you know what? We're limited by budget. We don't have resources to study every element in the population. We normally take a sample. The moment we take a sample, of course, we are going to have a numerical estimate of the sample that we call statistic. If we're looking for average and we settle for mean, like, because it's not only mean, we talk about measures of average, you got mean, median, mode, but how am I going to justify, computing mean? Of course, I'm going to justify that if I have a way to investigate the characteristics of that, And what we're trying to do here, what are we going to do to ensure that the sample mean, is just going to be concentrated on the population mean? How are we so sure? How can we guarantee the closeness of the sample mean to the population mean? The population mean is actually the unknown parameter value, which is the true value of the parameter. So how can we actually guarantee the closeness of the sample mean that we got to the population mean? That is where the idea of the law of large number is going to come in. And the law of large number is just going to say, okay, when you increase the sample size infinitely, we expect your sample mean to converge to population mean, okay, with a very high probability. And of course, that was why the idea of Chebyshev inequality came into the picture. We use Chebyshev inequality to figure out the probability of the absolute difference between the sample mean and the population mean, okay, within certain value of the standard deviation. Okay, that is what we always why we need the Chebyshev inequality. I demonstrated that, and of course in the last class I was able to prove the theorem that, okay, the moment our sample size is large, okay, we actually expect the probability of the absolute difference between the sample mean and the population mean, which is the true values of the mean, to be less than epsilon. The epsilon is just going to be a value within the standard deviation of the mean. Okay, and that was proved to be equal to 1. So we use Chebyshev inequality when we actually want to compute the probability of convergence of the sample mean to the population mean. Okay, that was what we did last time. Now today, yeah, which I've already reviewed. Now I want to go into today's topic, something related to normal, and I'm going to start from here. This time around, we know the distribution we're working with. Up to this moment, maybe probably we did not know the distribution. In statistical analysis, if you want to conduct a study in a population and you identify your random variable, it's either the population distribution is known or unknown. It doesn't matter. If it's unknown, we can conduct a statistical study. If it is known, we can conduct a statistical study. Okay, now we are assuming, okay, we are working with a random variable, a univariate. When I say univariate, I mean one measurement at a time. Maybe I'm talking about blood pressure or talking about income, or I'm just focusing on a particular variable at a time. Okay, suppose that y now follow normal distribution, okay, with two unknown parameters. Okay, we got mu, we got the variance, right? Sigma squared. Okay, of course, mu lies in real number, and the standard deviation is non-negative. Okay, now if there exists a constant a and b in such a way, we have a new variable s. The new variable s can actually be expressed as a whole variable y. You remember this is a linear combination. I gave an example the other time. Okay, if s is a total cost, okay, and if y actually stand for the number of quantity you produce, stuff like that. Now, of course, using the linear combination, if you take a look at this guy now, let me see if it's gonna, oh, it's not showing. So I'm writing something here, it's not showing. Okay, I'm gonna do, okay, so when you take a look at you want to figure out what is the expected value of x. You have x, the distribution of y, okay? We believe if y follow normal distribution, okay, and x is a linear combination of y, X is also going to follow normal distribution. Now we can find the expected value of X, right? The expected value of X is just going to be, okay, A, right? Okay, expected value of Y, right? Expected value of Y, okay. What is the expected value of B? B is a constant, right? Expectation of a constant is just going to be a constant, right? Now it's going to be A expected value of Y plus B. And of course, the expected value of Y is mu. Okay, so the value of Y is mu. Similarly, we can also obtain the variance of X. Okay, of course, if you want to obtain the variance of X, okay, the variance of AY, that's going to be variance of AY plus B. The variance, and if B is a constant, the variance of AY plus B is just going to be variance of AY, because the variance of a constant is 0. So the variance of AY is just going to be, where A is a constant, it's just going to be A squared variance of Y. And what is the variance of Y? Sigma squared. Then I'm just going to have A squared sigma squared. That's what you're going to have for the variance of X. Okay, so if that is what you're going to have, we now want to take it to a new level. We actually want to take this guy here to a new level where we want to express A as a function of the two parameters of the underlying distribution. We also want to express B as a function of the parameter of the underlying distribution. And right here, we are letting A to be 1 over sigma. Where is the sigma coming from? The sigma here is the standard deviation of Y, okay? And if we let B to be negative mu over sigma, by the time I plug in, that expression for A and B into this, I'm actually going to have this guy here. Oh my God, when I have that guy here, that resemble something that we know in statistics, where you have X equal Y minus mu over standard deviation. That very Z is going to be a standard normal variable, which is going to follow standard normal distribution. Of course, in statistical theory, when Z follow a standard normal distribution, of course, the mean of X, is going to be 0, and the variance is going to be 1. I told you the other time the reason why we go from normal distribution to standard normal distribution, because if we have different set of data set that follow normal distribution, they're actually going to have different means, different variances. Of course, if you want to figure out the probability of a variable of interest that follow normal distribution, then you actually need an infinite number of statistical tables. And therefore, for us to limit the numbers of pages that will be committed to statistical table, of course, we need to standardize and restrict the values of the mean and variance, to mean to 0 and variance to 1. And that is the essence of that. Okay, we want to go from there now. We know that that's a standard normal distribution. The standard random variable, this is based on a random variable Y. Now we want to move to something else. So moving to something else, we want to consider by theorem 6.3, check the textbook for theorem 6.3. If we have Y1 up to Yn, follow normal distribution. Don't forget what I mean by IID. Okay, the IID is just telling you the Y1 up to Yn are independent and they are being sampled from the same distribution. Okay, now if they are being sampled from the same distribution, you know what? We're interested in figuring out the average. Y1 plus Y2 up to Yn divided by N. Now, when you take a look at this guy now, okay, because we're choosing from that distribution at random, okay, if I have 10,000 investigators going into that same population, okay, or choosing sample at random, even if they choose the same number of sample at random, you're actually going to get different means. Me now become a random variable. And if me become a random variable, we want to find a particular values of the mean. that represent all other means, then I'm going to be considering the expectation of the y bar, expected value of the y bar. Then if I want to tell how reliable is y bar, okay, then I need the variance of y bar. Of course, which means if I know the expectation of y bar and I know the variance of y bar, then I can actually, conclude on the distribution of y bar. Because the distribution of the y bar, if I want to write that, I need to know the mean of y bar, and I also need to know the variance of y bar. So if you want to follow the theorem here, what I've given you before, I need you to perceive this guy. Why, if you want to rewrite that, that is going to look like 1 over n1 y1 plus 1 over n2 y2 plus 1 over n3 y3 up to 1 over nn yn, but the 1 over n1, they are all constants. They are the same all true. Okay, I wanted to take a look at this. I needed to take a look at what I have here. The AI is 1 over n in this case. 1 over n is the same. What am I using 1 over n? Because when you are computing the mean, you are assuming the variable has equal contribution in terms of weight. They are equally weighted. That's why you divide it by n. Each y1, y2 up to yn, they got the same 1 over n. That's what you're using. Now, you know that the sum of that is just going to be, if where A1 up to A2 are the same, imagine if A1 up to A2, A2 up to AN is the same, I'm just going to have A. If I have n number of that, that's going to be N, A, okay? And Y1, Y2 up to all of that, I'm just, going to have, you're having the sum, okay? So this is more or less, when you take a look at what I have here, right? Summation AI, yi, where A is constant, I'm just going to have N, A, Y, N, because that one is constant. So now if you want to look at the variance, you're actually going to have this. But A1 is 1 over N. A2, 1 over N, all the same. It means I'm just going to square. It's going to be 1 over N squared. Then I'm going to have variance, the sigma 1 square, sigma 2 square to sigma n square. But you know what? The sigma 1 square, they're going to be all equal. Why is the variance equal? Because they are identically distributed. So from here now, I'm just going to have n sigma squared. The variance of this is going to be n sigma squared. Okay, that is for the summation. Okay, now, which is actually what I have. Now, if I now want to go into getting the mean of the mean, the mean of that, then I can, for us, take a look at this. If I have y1 up to yn, that comes from a normal distribution with the variance mu variance sigma squared, and I know my estimator is actually this guy. If I have so many of that guy, where y bar becomes a random variable, I can boastfully say expected value of y bar is still going to be mu. Okay, I'm going to demonstrate that. If I have y1, okay, give me 1 second. I want to try this. Give me 1 second. I'm going to try this now. Oh, it's not supporting that. Showing here, not showing here. It's only those who are going to watch the recording. Okay, let me just stop that. Oh, let me see. Now I would like to make use of my whiteboard. I don't know why that. Maybe I'm going to call the tech later. But let me see if I can fix that. If I want that guy to go, discard that, and I just want to share my whiteboard. I just want to share my whiteboard. Let me see what is going to happen. If I share my whiteboard from here, and I share the whiteboard, is it going to show? The whiteboard is not showing, but it's showing on the Zoom, not showing here. I think I'm gonna call the tech later because as time goes on, I may want to write. So let me just go back to the lecture and see. I'm gonna go back to the lecture. Okay, so I'm gonna go back to the lecture. Let me see. Okay, so what I'm trying to say here is if you have y bar 1 and y bar 2, let's say you have two means, right? And I want to find the average of the means, right? The average of the means is just going to be what? It's just going to be y bar 1 plus y bar 2 divided by 2. What am I doing? Maybe I only computed two means, right? And the average of that. And you know what? Expected value of y bar is mu. And they're going to be the same as that of y2. So this guy here, okay, is what is going to be equal to mu. Why? Because this guy, expectation of y bar is mu. Expectation of this guy is also mu. So I'm actually going to have 2 mu. And 2 mu divided by 2, that will be mu. It doesn't matter whether, it depending on, whatever sample size. Why, if you have 5 means, okay, by the time you add y bar 1 plus y bar 2 plus y bar 3 up to 5 divided by 5, it's still going to be mu all the time. Okay, now, which is what you have here. Okay, now, what about variance? I want to find the variance of this guy. I want to find the let me clean up so that I don't confuse you. Now, you know what I want to do now? I want to find the variance of y bar, which is going to be finding the variance of this guy here. 1 over n is a constant, right? By the time that comes out, what are you going to have? 1 over n squared, right? Right? 1 over n squared, right? And when you summation y is y1 plus y2 up to yn, which is going to be sum of the variances. What is the variance of y1? Sigma 1 squared. Variance of y2, sigma 2 squared. Don't forget all the variances are going to be equal. So if I have sigma squared in n term, what am I going to have? That will be n sigma squared. Right? What is going to happen? N cancel n. That will give me this guy. That will give me sigma squared over n. So the variance of y bar is sigma squared over n. And the square root of that is the standard deviation of y bar that we call sigma over square root of n that we use in statistical analysis. Okay. Now, let me tell you the reason why in statistics we believe in the power of average. I'm going to say that again. In statistical analysis, in statistical framework in general, we attribute more power to the mean. And I'm going to tell you why. Let's consider this situation. Take a look at this. I have a random variable y that followed normal distribution. And this is the shape, right? Symmetrical. This is best shape. This is the center, right? And we got deviation from the center. What you can see here is a mu minus, z sigma. Okay. The z sigma just going to tell you the number of deviation from the center. Okay. If I'm no longer considering y, and what I'm considering now is actually y bar. okay, where y bar is a random variable, okay? Now, the distribution of that is also going to be normal, but you know what? If you compare these two, one is more spread out, and when you take a look at the second one, oh my God, there's a kind of, when you take a look at the variation here is very, very small. When you look at the variation that you see in that of the y bar, okay? And can somebody tell me for extra credit? Can you tell me the situation under which these two, they're going to be equal? What is that situation under which the two will be equal? Go ahead. The very large n, right? That's where they're going to be equal, right? There is one here that is supporting large n, and the other one is not supporting large n. You're very close. Oh my God, good job, good job. When n equal to 1, you're going to have this. So that guy is the one that actually supports you getting more than one trial. And as you can see, the standard deviation here is sigma, right? But the standard deviation of the y bar is sigma squared over root n. With sample size equal to 1, they're going to have the same deviation. But let me tell you, the moment sample size is greater than 1, that is going to be better than this. And that is what justify that, using that in statistical framework. Okay, so take a look at that here. Y follow normal distribution, okay, with a mu, that mu as a mean, the variance of sigma squared, but y bar follow normal distribution. What is the similarity? The similarity is that they got the same mean, but different variances. That is the difference between them. And what are we looking for in statistical analysis? We acknowledge the fact there's going to be error, but if you can minimize that. So that guy over there minimized that in terms of reduced variance. Okay, now, I now want you to see, you remember the other time, we use Chebyshev for convergence, right? Let me tell you this. We can use Chebyshev, you can use Chebyshev rule for convergence to compute probability, and we can use empirical rule. But let me tell you this, when do we use Chebyshev? When we realize the distribution of the random variable is not normal. When do we use empirical rule? When the distribution of the random variable is normal. And let me tell you this, situation where the distribution of the random variable is normal and you use Chebyshev, okay, that result will not have a very strong statistical power compared to you using empirical rule. Because empirical rule is more appropriate, okay, when the distribution of the random variable is normal. Why Chebyshev is more appropriate when the distribution is not normal. Does that make sense? Now I'm going to demonstrate now. Take a look at this. I want to talk about using empirical rule, using between empirical rule and Chebyshev inequality. I'm going to say this again. When the distribution of the random variable or the distribution of the sample mean is non-normal, okay, Chebyshev rule is appropriate. But when it is normal, empirical rule is appropriate. Now, what do we want to figure out? Like, what do we want to find with Chebyshev and with empirical rule? We actually want to know what is the proportion of the observation that lie within case standard deviation. If I want to find what is the proportion of measurements, okay, that lie within, okay, the case standard deviation, okay, then I can use Chebyshev rule if the distribution of the measurement is not normal. But I can use empirical rule if the distribution of the random variable is normal. Now, I want you to take a look at this. What I circle right now, if I want to use Chebyshev, oh, if I want to use Chebyshev now, here we want to find the probability of absolute difference between y bar and mu less or equal to 2 sigma over square root of n. In that situation, that 2 is k. 2 standard deviation, that's a k. You remember in Chebyshev, we got k, okay? The standard deviation, k multiplied by the standard deviation of the random variable. The standard deviation of the random variable here is sigma over root n. Don't forget, what is the random variable here? Y bar. Does that make sense? If I want to find that, which means I want to use Chebyshev to compute the proportion of observation that will lie within 2 standard deviation. If you want to do that, you remember, that would be 1 minus 1 over k squared. What is my k? 2. That will be 1 minus 1 over 2 squared. That will be 3 over 4, right? 75%. Now, I want to say this. I want to say this now. With the Chebyshev, okay, the proportion of observation lying within 2 standard deviation, okay, at least 75% of the observation. But if you want to go by the empirical rule, it is not 75%. Can somebody remind me? If I want to go with the empirical rule, what is the number of observation? What is the proportion of the observation that are within 2 standard deviation? Yeah, 95%. Send me a message for extra credits. Okay, now take a look at the 2. This guy said minimum of 75%, Chebyshev. But the empirical rule said 95%. Which one is weaker? The Chebyshev is more weaker. In a situation where if the random variable follow normal distribution, if you use Chebyshev, instead of you to use empirical rule, okay, you're actually going to get a result that could mislead. Because that may not reflect reality. It is not all the time that Chebyshev guarantee the true value. Does that make sense? Okay. Now, if I now want to go, if I now know the distribution to be normal, I'm not going to go by the way of Chebyshev anymore. What I might want to do now, if you take a look at what I've done here with the Chebyshev, you can compute the proportion of measurement within 2 standard deviation, within 3 standard deviation, depending on the, when k equal to 2, that is 2 within 2 standard deviation. If k equal to 3, within 3 standard deviation. But if you know the distribution of the data, okay, now this is what we have. You know what we're going to do? We're going to divide both sides by the standard deviation of the random variable. When you do that, that is going to give you this. Oh, what do I have in the absolute? That is standard normal. There are 2 forms of a standard normal distribution. There is one that involves random variable y, and there's another one that involves random variable y bar. Let me remind you. We got a z. We can have a z equal y minus mu over standard deviation. We use this guy here for z if the random variable is y. But what if a situation where the random variable is mean? Y bar minus mu, but the standard deviation is just to be square sigma divided by the square root of n. Does that make sense to you now, everyone? You remember I showed you the other time, right? Now, where are we now? The whole of this guy here now, this guy now is z, which is this guy. When I have the probability, the probability of the absolute value of z less or equal to 2, if I want to rewrite this, I already know the z is standard normal distribution. If I want to rewrite this, it's just going to be -2, right? less than equal to z less or equal to 2. I can make use of my normal table where you're going to, for those of you that use R, P norm of 2 minus P norm of negative 2. With that, what I'm trying to tell you, what you're going to get here, when you do that, what you're going to get here, somebody said it the other time, is 0.95. That was how we realized that 95% of the observation will fall within two standard deviation, but Chebyshev was giving us minimum of 75%. Why the normal give us, empirical rule give us give us 95%. Now, you can try this for 3 standard deviation and so on, but let me just quickly tell you the difference. Chebyshev inequality will only give us the minimum proportion of the observation, minimum. That's why you say greater or equal to at least. But the empirical rule will give you the estimate. There's a difference between estimate and minimum. Okay, so take note of that. Okay, now we got a question here. Okay, when you take a look at this question, a botany machine can be regulated so that it discharges an average of mu 1 cc per bottle. It has been observed that the amount of fuel dispensed by the machine is normally distributed. You know the distribution here. With sigma equal to 1 ounce. A sample of n equal to 9 feed bottle is randomly selected from the output of the machine on a given day. Okay, now here they ask you to find the probability that a sample mean will be within 3 ounces of the true mean for the choosing machine setting. You know what I can do in exam or in the meantime? Even though I know it's following normal distribution, I can ask it to compare Chebyshev and empirical rule here. Does that make sense? I can ask it to compare that. But right now, this is what you want to find. That is interpretation. Okay? You're told less, the probability that the sample within is 0.3. Within, that is the probability of the absolute, the difference between the sample mean and that. With that, you can use a Chebyshev, right? If I want to use a Chebyshev, I'm going to equate 0.3 to what? K sigma divided by root n. When I equate that to K sigma divided by root n, what do I want to figure out? I want to figure out K. Don't forget, you have the sample size, you have the standard deviation, you can find your K, and the moment you find your K, you're just going to substitute that in 1 minus 1 over K squared. But right now, if I don't want to use Chebyshev and I want to use empirical rule, okay, then I need the mean of the mean, I need the variance of the mean, which is what I've done here, because I want to use the idea of a standard normal. Okay, that is why I'm proceeding this way. Take a look at that. You see that? Okay, it's 0.3. I'm going to divide both sides by the standard deviation of y bar. And the variance of y bar is 1 over 9. The standard deviation of y bar is going to be square root of that. Take a look at that. That's what I have up to deduction. When I simplify that, then I want to find the probability of the absolute value of the z less or equal to 0.9. I can obtain this using the statistical table, and that is going to give me that. I can also ask you to use Chebyshev here too. Determine your K and plug in the values of K into 1 minus 1 over K squared and compare, because this guy is telling me 63.18% of the observation will be within that 0.3 that we talk about. Okay. We can also ask a question that has to do with sample size determination. If I'm anticipating, if you take a look at this question here, right? A sample size of 9 leads to 0.6318 probability. What of it is equation whereby I want to determine the sample size. If you take a look at this, I'm interested in the sample size that will enable me to get 0.95. Okay. And I'm still figuring out. Why figuring out? I'm trying to say, what sample size am I going to get if the probability of the absolute difference between the Y bar and the mu is going to be within 0.3? And that probability will be 0.95. Okay, I'm afraid if I want to increase my probability from 0.6318, okay, if I want to increase that, then the sample size is going to go up. And that's what I'm finding here. That's what I'm trying to find here. That's what I'm trying to find here. I'm trying to figure out what the sample size is going to be. Okay? And in the end, the sample size is 42.68. Then we're going to round it higher. That will be I need 43 sample size. Any question on this? Any question? And that was why I said, you know, that Y bar to be within is 0.3 ounces of mu with at least probability 0.95. Then I need at least 43 sample size. Any question? Okay. Now, of course, this is normal table. Imagine if we did not standardize, there's going to be so many of these. But because we standardize, we're able to just one page for standard normal table. Okay. Now, I quickly want to show you this. When you are talking about empirical rule, okay, 68% will be within one standard deviation. If that means if data set follow normal distribution, and you want to figure out what is the percentage of the measurement that will lie between one standard deviation, of course, it's going to be 68%. Two standard deviation, 95, three standard deviation, 99.7%. This is empirical rule. We apply empirical rule when the distribution of the data set is it's normal, symmetric, having a bell shape. Okay. Now look at that of the Chebyshev. What do you see? This is not a bell shape, right? Okay. Now for at least 75%, that is for two standard deviation. At least it's 8.89%, that will for three standard deviation. Oh, something is missing now. What is missing? Can we calculate when k equal to 1 for Chebyshev? What is going to happen? Remember, for Chebyshev, 1 minus 1 over k squared. What happened? When k equal to 1, 0, right? Because of that, to use Chebyshev, k must be greater than 1. But which means you may not be able to figure out if you're interested in within one standard deviation using the Chebyshev. It's not going to make sense because it's going to tell you minimum 0%. Take a look at that. This is Chebyshev. Okay, so take a look at that. Oh my God, this is going to be the end of the party. So what are we going to have next? What are we going to have next week? We're going to talk about central limit theorem next week. The whole of next week is going to be committed to central limit theorem. Let me tell you this. There's a difference between central limit theorem and the law of large number. The law of large number is focusing on you having a large sample size. When you have a sufficiently large sample size, you expect your sample mean to convert to population mean with high probability. But we have not talked about the convergence of a distribution to normal. And that is what we're going to do on that central limit theorem. The central limit theorem also going to rely on the law of large number, where we believe when the sample size is sufficiently large, even if the distribution, underlying distribution of the population is not normal, but if the sample size is large, there will be a convergence. Okay, that distribution will converge to normal. Okay, that is what we're going to do under central limit theorem. Start next week. Now, this is the end of the second week of my lecture. What I always do after second week, I want everybody in this class to send me a feedback. What you have learned, your understanding of what you learned in week 1 and what you learned in week 2. I need you to rate your understanding of what you learned in week 1 from 0 to 100%. Let's say, for instance, if your understanding is less than 100% for week 1, then tell me what you are struggling with. And I'm going to reply your message. Then for the week 2, also rate your understanding. Now, what I'm telling you now is I value feedback a lot. It's not compulsory, but to me, it's very essential. I want to hear from you. Okay, but because I know we live in a probabilistic world where I don't understand the degree of assimilation to be the same. I know some of you may get stuck and maybe you don't want to ask questions in class, but I want to hear from you. Okay, in the absence of, is there any question? Go ahead. Oh, you want to ask a question? Okay. Now, this is being recorded. If the quality of the recording is fine, of course, I'm going to put this on the YouTube. Okay, the moment you put my name of the YouTube, but I'm not going to post if the quality is not, if it is poor. But because after I used to watch it and I watch, I see if it's okay, then I put it on the, that will give you another opportunity, to be able to catch up with. Finally, statistics is very, very easy. Or what I'm going to advise that you should do, pay attention to notations, relate that to real life. The moment you relate to real life, you will understand. Like right now, I'm talking statistics because I relate every notation, every equation to real life. If I read any complicated maybe equation and I don't really understand, even if I understand mathematically, and I don't understand how it relates to real life, then I don't understand it. That is my belief. It is until I have a very strong conviction that I can relate this to real life. I remember what I used to do in Africa. When I'm learning this, then I will now go to my grandma. My grandma doesn't understand. My grandma doesn't go to school. In fact, my mom doesn't go to school. If I can explain to my mom in a language and my mom understand, then I understand it. So that is what I wanted to be doing, like trying to relate, follow whatever we do with mathematical, with analytical mind, not only mathematical mind. You can do it mathematically, but apply it into the real world. Okay, make sure you all stay safe and enjoy your weekend. Bye for now.